And here's kind of the rundown. So the average over the whole thing, 77%. Okay? And the breakdown, the way it worked, we looked at these the other day. First multiple choice was 57, went up to 82. Of course, the next time we take an exam, the second Scantron is going to be way higher than that. I just know it. Okay? So the average, that gave us the average of the multiple choice at 68%. The average for the fill-in part is 89%. Okay, so basically as a group, you guys kind of kicked butt on that part. So that was really good. I will pass them back today. And so if somebody will let me know with maybe 15 minutes left, then we can do that. I'll probably get so immersed in just blabbering up here that I won't notice what time it is. So if somebody will just point that out to me, interrupt me or something, then I'll pass them back. So what I'll also do, I haven't done it yet, is I'll post the keys to the exam. And once I've posted the keys, remember that you have 1 week to come and talk to me about points. Okay, if you think this grading, maybe something's not fair, or we added it up wrong, or entered it wrong, or any of that kind of stuff. But after a week, then we want to just be set on what we have. Okay? All right. Any questions? Okay. So remember to get your homework done this weekend if you haven't done it yet. Right? So it's due on Monday, and the next SI is today. Right? So there's an SI right after class. So you'll have your exams. We got some new material, though, you guys will be able to talk to. And I just want to, remind you, that really, the best way to study for this class is just study some every day. Go to those SIs if you can. The worst possible thing you can do is fall behind and try to cram at the last minute for the exams. Okay, so just stay up with it. If you scored really high on this fill-in, that's awesome, but don't get overconfident. Okay? Remember that a good portion of this exam was essentially review, was Gen Chem from the beginning. So from now on, we're not going to be seeing anything that we've done before. And as I've told you before, our material will just add on and add on and add on. We just build on top of it. Okay, so make sure you stay up with it. Okay, so we've been talking about isomers. Here, let me just point out a few things first. So there was I'm going to put a little box right here. So there's a few ways that come up that people draw things out that we just like to point out, so we didn't really mark these kind of things wrong, but just like to clean things up a little bit. So for one thing, remember that, and I didn't really see much of this at all, right? That we don't do these kind of structures where we just have these carbons like this, right? What was it? It was uncool, exactly. What we also don't really do, so if we have a ring like this or something, and we have a bond and we want to add an alcohol to it, okay? What we should do is we should try as much as possible to draw the bond to the actual atom that it's connected to, okay? So if I'm going to draw an OH onto this side that's on the left side of the molecule, I should actually draw the bond to the oxygen, okay? And then we can put the H over here, all right? So to do it like this, it's just not cool, all right? And of course, that's one of our most important things that we want to try to do in here, right? Chemistry is really cool. Organic chemistry, let's narrow that down a little bit. Okay, so along with this, if we have something like, why is this drawing? Like a methoxy group, okay? So when we do that again, we want to draw the bonds to the atoms they're connected to. And then if we do it, usually if I go this way, I'll even do CH3, okay? So this shows us the bond goes from a carbon to an oxygen to a carbon, right? Other ones like that, let's see, I saw some things like this where, and even if we drew an isopropyl, you can either just do it like this, or you could do it CH with CH3s, right? But it's not as good to do it like this and just have it kind of be, how do we do this? CH3, two of them, like that with this bond just going into the middle of that whole thing up there, okay? So attach it to the actual atom that it should be, okay? And it just works out better, all right? So this isn't so good. All right? Just a few little things. Everybody got it? Okay, so let's go on. So we're going to start out just by finishing up a few problems that were of a type that we started on yesterday, right? So we were just comparing molecules. We were deciding whether we had four different possibilities. They could be either the same, they could be constitutional isomers, they could be enantiomers, or they could be diastereomers. Okay? So, let's just continue through these and just add a few more problems to our repertoire, our experience. Okay, so those two at the top, anybody know what general kind of molecules those are? They're cyclo, all right, but general kind of, they're sugars, okay? They're just simple sugars. In fact, this one over here is the one that I know right off the top of my head. This is glucose. Okay, so that's a sugar that our bodies use in our blood, so blood glucose level and stuff. That's what our brain uses. That's what we use for energy. Okay, and I think this other one is probably galactose, but I wouldn't bet my life on it. Okay. But since we're not doing biochemistry right now, we don't have to worry about that. So what's the relationship between those two molecules? What's important here? Do we have any asymmetric centers? Yeah, we got a bunch of them, right? We got one here, we got one here, we got one here, we got one here, and we got one over here. Okay? So, what's different between these two molecules? Right, there's just one alcohol that's different, right? So in one case, I heard it, this alcohol here is in an equatorial position, right? Equatorial with an A. I saw about 1 million of you put it with an I in there. And this one over here is axial. Okay? So, do you think that position can just interconvert? Go back and forth? Can it just easily go back and forth between those two? No, can't, right? Because remember, if we have that equatorial alcohol, we've got an axial hydrogen, right? And if we have the axial hydrogen, we have an axial alcohol, we got an equatorial hydrogen. Okay? So, we have all the other places are the same, right? And we got only one that's different. So what does that make the relationship here? Diastereomers, right? Right? Because we have some chiral centers that are the same and some that are different. All right? Okay, what about the next two? Diastereomers? Well, we could rotate this one around, right? We could rotate this around to try to... So I'm just going to rotate the top and the bottom around like this. We'll make the chain go the same in both. Okay, as we rotate these OHs around from the top down to the bottom, are they gonna still be dashed, or are they gonna be wedges now? I'm just gonna rotate it in the plane. They're still gonna be dashed. Okay, so I'm not gonna flip it over. I'm just gonna rotate it in the plane. So these are both like this. And what about the methyl group? It's going to be dashed as well. Okay, so now compare this one with the one on the left. What do we think? Okay, anybody? All right, are they the same? No. Are they stereoisomers? Yeah. Are they mirror images? No. Then what are they? They're diastereomers. Are they chiral? No, neither one is chiral, right? Why not? They have symmetry, right? So there's a plane of symmetry that goes right down through here or right down through here. So they're both achiral. This is achiral. But they're still stereoisomers of one another. And because they're stereoisomers that are not mirror images, they're diastereomers. Yeah?
One of the alcohols in the bottom were a wedge instead of the dash.
Mm-hmm.
Would it still be achiral?
Okay, so good question. So the question was, what if we had instead something like this, where we say had a wedge here, dashed over here, and then either a wedge or a dashed up here? Would this be chiral? Yes, this would be, because there's no longer a plane of symmetry. Okay? This one is chiral. Okay, so these two up to in the middle on the left, they're both achiral, right? But do they have chiral centers? Yes. So what do we call them? These are both meso. Right? Molecules that have chiral centers, but that are achiral because they have a plane of symmetry. Okay? What about the bottom two? How many chiral centers do they have? One, right? Can they be diastereomers with a single chiral center? No, they have to have more than one. Okay? So, are they constitutional isomers? No. So that we got two possibilities, right? Same or enantiomers? So how should we tell here? Okay, we could say rotate this around this axis, kind of like that, right? And we could get something that looked like this, right? And then on the third one, so when we rotate that methoxy group down to the other side, is it going to be a wedge or a dashed line? A wedge, right? We're going to rotate it around. Okay, now what do we think? They're enantiomers, right? Because they have a single chiral center, and that chiral center is opposite. Okay? We could, how else could we tell? Yeah, we could. Yeah, we could do the R and the S, right? And so, and notice that in both cases the number 4 is coming forward, right? So we could do this 1, 2, 3, right? Here's H. This is 4. So is that R or S? Right, it's S, right? Clockwise rotation, but number 4 is in front. Okay, what about the other one? 1, 2, 3, H is 4. R. So counterclockwise, we reverse it because number 4 is in front. We have S and we have R. We have a single chiral center and it's opposite, so they're enantiomers. Okay? Yeah, question?
Are there patterns of reactivity when dealing with constitutional isomers or enantiomers or this?
Okay, so the question is, are there some patterns of reactivity if we have different constitutional isomers, enantiomers? Constitutional isomers, certainly. But we'll have to go through and we'll have to look at each of the functional groups and we'll have to make those trends as we go. We can't have one huge, big, overarching for everything. Enantiomers is harder because enantiomers will only have different reactivities if they're in the presence of some other chiral group. Like I think I mentioned before, if one enantiomer is reacting with a chiral molecule, a protein or something, then one can react and one may not. But I'm not sure that there's really a pattern on that, though. Okay? All right, so go on. So we got one more topic we need to talk about with stereochemistry, and that has to do with, how do we actually tell these things apart? If we have a pair of enantiomers, they're essentially the same. How do we tell them apart? Okay? So let's just think about the physical properties of enantiomers. So here I've got the two mirror images down here on the left. As long as these are in a, let's put right here, non-chiral environment, means essentially they're not reacting with something that's chiral, all right? Then pairs of enantiomers will have the same, basically, everything, okay? They'll have the same melting points, boiling points, polarities, solubilities, reactivities. All of those they'll be indistinguishable from one another, okay? The differences, though, come when we have them in some type of chiral environment. So it could be reacting with another chiral molecule. And you can think about that is if we have some, let's do it in just a kind of an abstract case, but let's say we have an R molecule here, okay? And it reacts with another R molecule and it gives us something like this, right? What if we had that same R, but it reacted with a molecule that was S? So we're taking one molecule with a single chirality and reacting it with the two different enantiomers of another molecule. All right? Then we get R and S, and if we compare these two, what would be the relationship between those two molecules? whatever they are, if they had two chiral centers, one that has R and R and one that has R and S, what's the relationship? They're diastereomers. Okay? Okay, so enantiomers have the same properties. And let's put it down here, though. Diastereomers, they don't have any mirror image relationship or anything. Okay? Diastereomers have different properties. They're just different molecules. Okay? So, if we can take one and then we do it with the two enantiomers, this is essentially a diastereomeric arrangement now between the top and the bottom. And so those interactions are going to be different. Okay? So, chiral environment, the common one, most important, is probably reacting with an enzyme. Okay, and another place that turns out to be important is in how they interact with what's called plane polarized light. And this is going to give us a way to distinguish one enantiomer from another. Okay, so just a little rundown on what plane polarized light is. Okay, so one way to think about it is that when we shine light, it's shining along this way. Light, remember, has these wave properties like this. And if we looked at it from the end on, we just see some line that's up and down like this. It'd be going up and down. White light like this is going to have these planes of this light all the way around. Okay, so we're just going to be dispersed all the way around. And so that's what they're showing here. So here's one plane of light, here's one, here's one, here's one. There'd be other ones in the middle and everything like that. So what we do is we take this normal light and we put it through what's called a polarizer. All right? You can think about it as just like maybe some slats or something like that. So or a grating or something, only light that's arranged in one plane can pass through. Okay? So here, only light in a single plane passes through this polarizer. So that's what it's showing then over here. All these yellow ones now, these are all these waves of light, and they're all only lined up all in one plane. So this plane polarized light has a single plane of light. All right? So we're going to use this plane polarized light as an experimental tool to analyze our molecules. Okay? So the way we do this, we'd have our light source here. We'd shine the light through here, through the polarizer. And so here's our single plane of light. And then we're going to send it through, this is our sample tube. Okay, so we probably have some solution with our molecule we want to analyze in a container here. And they're usually tubes, and the light can pass right through. Okay, so if this is an achiral molecule, then the light will pass through unchanged. Okay? So achiral light is unchanged. Okay, we'd call this optically inactive. Okay? It turns out, though, that if we shine this same type of light through a chiral molecule, because there's no symmetry around the molecule, it's asymmetric, the light essentially interacts with one side of the molecule differently than the other side, and it causes the plane of the light to rotate. Okay? So it goes through the same way as we did before, but now we have this chiral compound, and you can see that the light, so here's how we started out with, and so the light has rotated some number of degrees. Okay, so it can rotate either clockwise, here it's rotating clockwise, or it can be counterclockwise. Okay, if it's clockwise, then we usually call it, I'm going to probably space out up here. Let's do the counterclockwise first. Sometimes we just put a minus, okay, it means counterclockwise. Or we can call it L, which stands for levorotatory. Okay, so we can think about this L as being left, right? So it's going counterclockwise, it's going to the left. Okay, if it's going clockwise, you can give it a plus or a D. And D stands for dextrorotatory. Thought I was going to forget, didn't you? I remembered it. Come on. Okay. Yeah, so that's clockwise and counterclockwise. All right, so we can, and then we get not only the direction of the rotation, but we can also get the degrees. Okay. Okay, it turns out that the amount of rotation caused by a chiral molecule depends on several things. Okay? It depends upon the concentration of that compound in our solution, right? You can just think about it that, the more molecules that it runs into, the more it's going to rotate, right? So the higher the concentration, the more the rotation is going to be. It also can depend upon the sample container really mostly in the length of this sample container. Okay? Just like with concentration, if you have the same concentration but you have a longer tube, it's going to run into more molecules as it passes through, and so that would increase the rotation. Other things that can influence it, but not in such a systematic way, are things like temperature and the wavelength of the light that we use. Okay? And those don't really have trends that we can follow, but what we do instead is we just report them. So this is the wavelength. So then, if somebody else wants to repeat our experiment, they want to use the same, type of light and the same temperature that we use. Okay, so because the amount of rotation depends upon mostly the concentration in and the length of the sample container, we don't usually just report only this alpha value, only the degrees of rotation. What we do is we normalize it for concentration, okay, and length of sample tube. Right? So what we do is we report something that's called a specific rotation. And the specific rotation, the way we can tell that it's specific rotation is that we put it in brackets, okay, rather than without brackets. Okay, so this is a specific rotation down here. We give the value, we say what temperature and what wavelength it is. Usually we use, I didn't write this down, we use what's called the sodium D line. And I can't remember exactly what it is, 500 and something nanometers. Okay, so here is alpha. So this is the experimental rotation. Okay. L is the container, we usually call it a cell, is the cell length, okay, usually in decimeters, okay, and we end up with decimeters because that's the normal length of a cell, okay. Usually the cell length equals 1 decimeter, right? 10 centimeters. Okay, so usually we don't even have to worry about that because it's always a 1. And then the concentration down here is usually in molarity. Okay? Sometimes it's in different units, but, you know, they'd be reported however. And so notice that the higher the concentration, right, we're going to get more rotation, but we're going to divide by that number, and so we're going to kind of standardize it here. So the reason we do this is then if I run this experiment here at Utah State and somebody else runs it, you know, down at the University of Utah, we don't have to get our concentrations exactly the same, but we should still come up with the same specific rotation, okay? All right, so this is the number that we usually report for chiral molecules, okay? If we discovered a new one, or if we synthesized one, you know, we'd report this as a value. All right, so a couple of details about the rotation. One thing that might be surprising is that the direction of the rotation, whether it's plus or minus, is independent of whether a chiral center is R or S. Okay? Not all R molecules go clockwise and all S go counterclockwise. Okay? They can be mixed up. And here's an example. These are pretty similar molecules. In fact, it's just an acid and its conjugate base, but lactic acid with the S chiral center has a plus rotation, so it rotates the light clockwise, right? Whereas sodium lactate, this is just the conjugate base of lactic acid, has the same chiral center, still S, but it rotates the light now to the counterclockwise. Okay, so I don't think that there's a real trend that we can pick up that we can predict this. We just have to do it experimentally. Okay? The one thing that we can predict, and this is always true, is that enantiomers, pairs of enantiomers, always give opposite rotation. So opposite and equal in rotation. Okay? So, for example, here we have this R2-methyl-1-butanol, right? And if it's pure and it gives a specific rotation of plus 5.75, and we take its enantiomer over here and do its rotation, it has minus 5.75. Okay, so enantiomers will give opposite rotations. Okay? But it's not always that R gives plus and S gives minus, right? If we have different molecules. All right? Okay, so not always do we have, if we have enantiomers, do we always have completely pure enantiomers? All right, we can have mixtures of enantiomers. All right, and so here, I guess I didn't write all this down. If we have a 1-to-1, mixture of enantiomers, okay. 15 minutes? Okay, thank you. Let me just finish this little bit right here. 1-to-1 mixture of enantiomers. This is a specific thing. We call it a racemic mixture. What do you think its optical rotation would be? 0, right? So its rotation would equal 0 degrees. Essentially, they cancel each other out. Okay, so let's look at this, what we call optical purity. We could use something called enantiomeric excess. Okay, so the enantiomeric excess, essentially what we're going to be analyzing is the amount of one enantiomer that's in excess of the other. Okay? So what we do, we can do this in two ways. We can look at the observed specific rotation, and then we can compare that to the specific rotation of a pure enantiomer. Okay? So essentially, if we had something like this, imagine that we had, let's see, we had, how do I want to do this? 33 essentially to 66, so, or whatever, 1/3 to 2/3, right? So half of this other one would get canceled out, right? So we take the minor one, if it rotates in one direction, it essentially cancels out the same amount in this other, of the other enantiomer, right? Because that would be, we took 33 of this over here, then we'd have 1-to-1, and that would be racemic part of it, right? And so we're only going to analyze that part which is in excess. Okay, so we can either compare it like this. So here's this enantiomeric excess for an example. If the observed specific rotation was 9.2 and the pure enantiomer was 23.1, you just multiply this out, you get 40% enantiomeric excess. Let me write it another way. We can say we can take one enantiomer, whichever one's in excess, subtract it from the other, and put it over the total. Okay? So again, and then times 100, this would also give us an enantiomeric excess. Okay? Just depends on what information we have. Okay, so that was the last bit. We've talked all about these isomers and optical purities. And so if a molecule rotates the light, we call it optically active. And that's a property of chiral molecules. Okay? All right, so let's pause this.